All right, so we have seen the biasing techniques for the bipolar junction transistors. We have seen three techniques at length, and one technique we have just glossed over. Today, we will start with unit number 2 in your syllabus, and that is the common emitter voltage amplifier. Now, when we talk about the voltage amplifier, this is where the actual working of the bipolar junction transistor is seen to be more better way. Okay, so I'll just start drawing the circuit. So we'll see that there is a similarity of what we have seen earlier. There are so many parts which are common. Remember, this is the common emitter configuration. This should not be new to you, whatever I am drawing right now. Yeah. So this is your. So what we are doing is we are biasing the network. We are biasing the transistor using voltage divider bias, or also called as the emitter current bias. All right. So this is your VCC.
Excuse me, sir.
Yes.
सर स्क्रीन शेयर नहीं हो रही है कोई भी.
Sorry.
सर स्क्रीन शेयर नहीं हो रही है.
Screen share नहीं हो रही. एक second. Do it once. Is it okay now?
Yes, sir.
Yes, sir.
Yes, sir. Visible.
All right. So okay. So this was your common emitter. Rather, this was the voltage divider bias, emitter current bias. Now you already know that biasing means we are just initializing the transistor so that then now it can work as an amplifier. Okay, this is RC, this is RE. You already know that this is R1, this is R2. Okay. In addition to that, we have some extra components over here, and those components are like these. So we have a capacitor here. Okay, we do have a capacitor here also. Look at the polarity of the capacitors. We have a capacitor here also. Okay, so this forms the amplifier. Okay, why we are going to have the capacitors like this, we are going to see in a couple of minutes. Of course, we have the load also, which is connected. So most of the times I show the load with a box like this, because this can be a resistive load or it can be a capacitive load. Call this as RL. We call this, here we get the output VO. Okay, then we have at the input, we have similarly we have to connect the source, that is the signal where we are supposed to amplify. So again, it is going to have its own internal resistance. Let us call it as RS, and you have the source, which we call as VS. All right. Call this capacitor as C1. Call this capacitor as C2. This as C3. This forms your common emitter voltage amplifier. Okay. Let us see the input and the output relationships. So first of all, this is time axis, this is voltage axis. Okay, and here we have the input and the output relationships. So let me put it this way. This is the biasing level. Okay, in simple plain terms, this is the Q point. So this is your VCEQ. Okay, and your input signal is like this. Okay. So now what will be the output signal? That is what we are interested in finding out. Since we call this as an amplifier, we are expecting to have amplification over there. So just for the sake of, let me see if I can. I'll have to draw it in the conventional fashion. So we'll see later on what this is about. Actually speaking, this VCEQ is the voltage is over here. Okay, I think you should not get confused. So instead of VCEQ, I will simply remove this all, and later on we'll talk about the VCEQ thing. Probably it may confuse you at this point of time. I'll draw a simpler figure. And I will show here from the ground level. So for this graph, this is the ground level, which is at the input, and the ground level for the output is a similar way. So that you will not get confused at this point. Okay, so consider this now as the 0 volts. This also has 0 volts. Now this is at the output here, VO. So this is VO, and this is your VS. Okay, right. So if your input is like this, oh God, drawing is getting worse every day. Okay, now in that case, let us have a look at what is the output. Okay, so this is the amplified version of your input. And what is the peculiarity that you see here? Yes, so this is the input, this is the output. What is the peculiarity that you see? Number one, it is amplified, and number two,
Phase is different, sir.
yes, it is out of phase with the input by 180 degrees. So these are the two important things that you have to note about the common emitter voltage amplifier, that the output is always 180 degrees out of phase. So VO is 180 degrees out of phase with the input. Okay. Now, why I'm calling this VS? Because there will be another part of the input which is going to appear at this point, which we are going to call as Vin. Okay. So this is how basically what is the relationship between the input and the output. Okay. Interesting things to note about this is that first of all, it uses the emitter current bias. Okay. Second point is we use bypass capacitors, bypass and coupling capacitors.
You have an idea?
Now, what are these bypass and coupling capacitors? C2, your C2 is called as the bypass capacitor, whereas C1 and C2, C3 are called as the coupling capacitor. Why do we require these things? Why do we require the coupling capacitors?
Coupling capacitor is
We'll
required
talk about, yes,
AC signal.
we'll talk about C1 and C3 first of all. Okay. Now please remember that your input signal Vs, there may be some DC content. What do you mean by DC content? Let me show you at this point of time. So your signal source may be having some DC content over here along with it, and your AC, your signal actually which we want to amplify, is riding on the top of this like this. So this is your DC content, and this is a very peculiar scenario. Okay, this is the voltage. Now, if you don't use the coupling capacitor C1, what is going to happen? If I don't use C1, what is going to happen? Yes, anyone can you tell me what will happen? If I don't use C1, if I directly couple this to the input over here, what is going to be the problem? Guys? Hello? Answer this question, please. What may be the problem if you don't use this capacitor? See, we have been very careful with deciding the Q point, isn't it? We were very cautious while designing the Q point. And what did we say about the Q point? What did we say about the Q point? We said that the Q point should be stable,
Stable.
isn't it? And if Q point changes or shifts, what is going to be the problem? We already know. All right. So already we are having this VCQ and ICQ set very cautiously. But who is setting that Q point? In our case, in this particular case of emitter current bias or voltage divider bias, this voltage VB is responsible for setting the Q point. We have already seen the design. Yes, agreed?
Yes, sir. Yes, sir.
All of you agree with this?
Yes, sir.
Okay. Now, what you are doing if you don't use C1, what you are doing is you are superimposing this DC content, I mean the signal with the DC content on this point, at this point rather. What is going to happen to VB? What is going to happen to VB? Let us call this DC content as VDC. So what will be the net voltage appearing at this point where we had VB? So what will happen to VB? This point. If directly I couple the DC signal, if I couple the signal which is having a DC content, what will happen to VB? The voltage now at this point will be VB plus VDC. Agreed? Agreed?
Yes, sir.
So
Yes, sir.
essentially, what are we doing? You are changing the Q point, which is totally undesirable. Are you getting this?
Yes, sir.
So we should not couple the DC over here. And that is the reason why we use capacitor, because what is the property of capacitor?
Bypass the AC signal.
Yes, it bypasses AC, but blocks DC. And we have already seen why it does that. Look at the impedance equation or capacitive reactive equation. XC is 1 upon Y square FC, so many ohms. If F is 0, what will be XC? F is 0 means what? We have DC. It is
Infinity.
your XC will be what?
Infinity.
Infinity. That is, it is open for DC. That means it blocks DC. Okay, and that is the reason why we use coupling capacitor at the input to block the DC content inside the input signal. Why? Because it may change the Q point. In a similar way, the output coupling capacitor is also used over there. Why? Because at the output of your amplifier, again, the output of the amplifier, your signal will be across VCE again, isn't it? And it is riding on the top of VCEQ. That was your Q point, and your signal was, your amplified signal will be, okay. If you want it this way, your amplified signal will be like this. So this signal itself is having DC content. Because of amplifier, it is going to have a DC content equal to VCEQ. And your load can be anything. It can be another amplifier. Load can be another amplifier. That is the reason why I have shown it as a block, a box, rectangular box, isn't it? So it may change the Q point of the next stage. Okay, we don't know. We don't know what will happen there because it is not within our control. Load is always set by the customer. Okay, so we cannot say. Can you please mute your mics? Somebody's mic is active. Okay. Okay, so what we have here is another coupling capacitor. So what this capacitor does, it will block this VCEQ, this DC level, from going towards the load side. So what we will be having at the load side is only the AC signal minus or without the DC level. This is the function of C1 and C2. C1 and C3. And that is the reason why they are called as the coupling capacitors. Now let us have a look at why we have the polarities here. We have specific polarities here, you see. Why? This is the positive side, this is the negative polarity of the capacitor. Similarly, positive polarity, negative polarity of the capacitor. Why is that so? Because we always know that this side of the capacitor will be at a higher voltage, DC voltage, that is VB is always going to be there. Okay, so that is the reason why this positive plate is connected to the VB. Similarly, here we already know that this is going to have VCEQ, always a DC content over there. Okay, and that is the reason why the positive plate is connected to this point. All right, these are very, very important things. Please make a note of it. Why the positive? What is the logic behind having typical connection of the capacitor? Are you getting this point? These are important concepts. I am repeating this again and again, that these are important concepts. If you miss these concepts, you are not going to understand the amplifier, and if you don't understand the amplifier, you won't understand electronics. So, as simple as that. Is there any question with this coupling capacitors at least? Yes?
No,
No,
I hope not.
No, sir.
I hope you are jotting down your own notes, whatever I scribble on the screen.
Yes, sir.
Okay. So we have seen the polarity of the capacitors also. So essentially what we can say that the coupling capacitors isolate the source and the load. Okay. As far as DC is concerned. So coupling capacitors will isolate the source and the load as far as DC is concerned. But we want the AC signal to pass through. Now another important thing is C2, capacitor C2. Very, very important. Now this capacitor C2, what do you think it does? Look at where it is connected. It is connected across RE. So for AC signals, this point will be ground. Why? Because you are having a direct connection to ground for AC signals via C2. So C2 is called as a bypass capacitor. What does it bypass?
AC signal.
It bypasses RE.
RE.
It bypasses RE. So the emitter of the transistor is literally at the ground level as far as AC is concerned. Okay. If it is not connected, still you don't have a problem while working, but the voltage gain, that which we are going to see in a short while, is affected drastically. So if bypass capacitor is not used, voltage gain reduces drastically, which is actually defeating the cause of using an amplifier. Okay, we want the voltage amplification. What we want to do is we want to amplify the voltage signal from Vs to Vo, where Vo value will be much larger than Vs. Normally Vs for small signal amplifiers will be in millivolts and Vo will be in volts. So that kind of amplification we want, and if you don't bypass Re, voltage gain is reduced drastically. Okay. Sometimes we have partial bypassing of RE also, but we won't go into that scenario. All right. So let us see another important concept, and that is the common emitter AC equivalent circuit. So how does the AC signal see this circuit? Is simply what we are going to see. So we have two variants now, one with bypassed RE and one with unbypassed RE. So first of all, we will see the bypassed RE case. How does the signal appear? How does the signal appear? How does the circuit appear to AC signals? Okay, that is what we will see. Now this is going to be very, very interesting, and of course, very, very conceptual. Let us see the circuit. So when I start drawing this, you also copy whatever I am doing. Now you'll be surprised to see that it looks very different. Okay, I'll draw this in different colors. So this is called as the equivalent AC equivalent circuit. Can you digest why it looks like this? Why it is called as AC equivalent? Because how the AC signal will see the circuit is what we are interested in knowing. So, but you will be surprised where is VCC and where is ground and why this is all done. Okay, so let us say something about it. For AC, does VCC and ground change? These values are constant. Agreed? VCC and ground are constant.
Yes, sir.
Okay. So as far as AC signal is concerned, they are one and the same. They are one and the same. For AC signal, VCC के हो या फिर ground हो doesn't make any difference because they don't change at all. They are constants. Okay. So look at the input side. What we have used here, what we had earlier in the circuit was this. I'll redraw it. We had the bypass capacitor and then we had the load connected here like this, and then we had the biasing resistors. This was your VCC. This is the ground. So when we say that VCC and ground are same, look at this point. This is R1, this is R2. Of course, let us not forget the source also. Okay, so when we draw the AC equivalent, basically the capacitors will act as short circuit. So you will not see capacitors in this figure. They are short circuited. All right. Is this okay?
Yes, sir.
Yes,
Once
sir.
you are short circuiting it, RE is also bypassed or short circuited. So you won't see RE here. Okay.
Yes, sir.
At the same time, look at the base of the transistor. Base of the transistor is connected to R1. Other end of R1 is connected to VCC. Okay. Here, one end of R1 is connected to the base and another end is connected to a common point, because we have already said that as far as AC is concerned, VCC and ground are one and the same. So this R1 and R2 literally appear in parallel like this, because this point is AC ground. Okay, this point is AC ground. So VCC, let us write it down like this. So VCC and ground are both AC grounds. This is very interesting. So R1 appears across base and ground. Remember now, this VCC is AC ground. R2 is connected to base and ground, AC ground. So if I reflect it here, one end of R1 is connected to base, another end is connected to AC ground. One end of R2 is connected to base, another end is connected to AC ground. Is it clear?
Sir, and what AC ground really means?
Please remember that ground is a reference point. We normally what we do is the lowest voltage point we call as the reference point, which we call as the ground. So somewhere here you can see here that I have connected the ground or the lower end of the AC signal generator, and that point is the AC ground. Nothing different. What we require is a reference point, and the lowest point naturally for AC in this case is this point. Why we have connected it here like this, and so this becomes your AC ground. And in addition to that, we have also said that VCC and ground are both AC grounds for AC signals only. Are you getting this now? Is your doubt clear? Very, very important. If not, you please ask me again. Because without this, you will not be able to understand any other circuits. So we can say that this circuit is called as the AC equivalent circuit. How the AC signal will see the circuit. Okay, let us have a look at the output side. At the output side, one end of RC is connected to the collector. Another end is connected to what?
BCC.
Another end is connected to
BCC.
VCC, and we have already said that VCC is a
AC ground.
AC ground.
AC ground.
You see here, exactly the same thing is happening. In fact, that is the concept. So are you clear about why I have drawn it like this here?
Sir, can you please explain once more for R1 and R2?
Okay. Where is one end of R1 connected? To the base. Look at the base of the transistor. R1 is connected to the base, one end. Another end, where is it connected?
BCC.
VCC.
And we have already said that VCC is nothing but AC ground. So R1 is connected to base and the AC ground. Similar is the case with R2. One end is connected to base, another end is connected to ground. And we already said that VCC and ground both are AC grounds.
ओके सर सर मींस जैसे कि सर पहले वाला जो था हमारा फिगर, सो एक एंड उसका वीसीसी से कनेक्टेड था R1 का, और R2 वाले केस में ग्राउंड से कनेक्टेड था. तो सर
Exactly.
मतलब जब हम ये एसी वाला बनाएंगे तो बोथ आर एसी ग्राउंड्स.
Both are AC
तो
grounds.
ऐसे
Exactly.
हाँ ओके
Exactly.
सर,
Exactly.
पैरेलल में. ओके सर.
Similar is the case with RC also. And why doesn't RE appear?
Sir,
It's
because the
shorted.
capacitor has
Yes,
short-circuited by
actually short-circuited by the bypass capacitor.
bypass
Similarly,
capacitor.
you can see here that the source is directly connected. Where is the capacitor gone? This capacitor वो कहाँ चला गया? ये capacitor भी कहाँ चला गया?
Short circuit.
Yes,
short
it is a
circuit.
short circuit for AC. It is a short circuit for AC. So this is called as the AC equivalent circuit for common emitter amplifier with bypassed RE. Another variant will be there. What is that? Another variant? We
Without
had two
bypass
possibilities.
RE.
Unbypassed.
Yes, CE AC equivalent which will be with for, let us say, for unbypassed RE. वो कैसे होगा? How will it look like? You're going to tell me now.
Maybe.
Emitter terminal
Okay,
ground जो है हमारा common
let me complete the input side first. Okay, then you.
सर emitter terminal जो common वहाँ पे आ जाएगा.
Okay. Just one sec. Hold on one sec. This is as usual R1, R2. यहाँ पे क्या होगा? Same thing. RC. यहाँ पे क्या होगा? The load. This will be your output voltage. Remember, our output voltage is always across collector and emitter. This will be your input signal generator, VS, RS. This will be your Vin. Yes, what is going to be the modification? Now RE is not bypassed. So where is one end of RE connected?
In the ground.
One end is connected here to the emitter, another end is connected to ground. Now this is not there. So where do I connect it? It will be like this. This will be your RE. Is that okay?
Yes, sir. Yes.
Very good. All right.
Yes sir.
Now what we are going to do is another interesting thing, because we want to analyze the circuit. Why we are doing all this? Because our objective is, your objective is to find out the voltage gain equation, the current gain equation. They are called as AV and AI respectively. We are supposed to find out the input impedance. We are supposed to find out the output impedance and the power gain. So these things are very, very important. That is the objective. We want to find out the voltage gain. We want to find out the current gain. We want to find out the input impedance, output impedance, and the power gain. Okay. So these are the 5 parameters which why we are doing all this. Okay. Now there are 2 different ways in which you can do it. But before that, let us go one step deeper into changing this circuit, replacing replacing. Have we done the H parameter equivalent circuits?
Yes, sir.
I think we have already done H parameter equivalent circuits in one of the lectures.
Yes, sir.
Okay. So replacing the BJT with its H parameter equivalent. So again we have two varieties, one with bypassed RE and one with unbypassed RE. Now my objective is to replace the bipolar junction transistor with its H parameter equivalent circuit. Can anyone tell me for BJT in common emitter configuration, what is the H parameter equivalent? Yes, what you have is a resistor like this, a voltage generator like this. I hope you remember these things. Then you have a current source. This is a voltage source, and we have an output resistance like this. So this is your emitter, this is your base, and this is your collector. We call this as what? What was the name of this thing? This component? Yes? Anyone? What is the name of this component? It is H. Yes? What is the name of that component? H I E. Okay, what is the name of this component? Guys, why are you silent? Why are you silent? You are not revising, it seems. I told you, I warned you right in the beginning. What is this? 1 by H O E. What is this? This is H R E V C E. And what is this? What is this?
HFE. HFE-IB.
H F E I B. Where this is your IB, this is your IC. So this is the H parameter equivalent of a transistor in common emitter configuration. Do you remember this at all? Guys?
Yes, sir.
No, nobody remembers this. Ena? I think somewhere one of the lectures we have done this. Yes. So that was 10, 11. Did we do this or not? Guys? Come on, students, tell me. In one of the lectures we did do this. Yes or no? Come on, say something.
Yes, sir. Yes, sir.
Yes.
We have seen these parameters. There was a separate lecture on H parameters, right? Okay, if you don't recollect, let me refresh it for you. When the transistor is in common emitter configuration, you can represent the transistor in terms of these four components. What are they? This is the input resistance, as if it is an input impedance or input resistance of the device. Then you have this part, which is nothing but a feedback. Some part of the output. Where is the output? Output is here, ECE. So some part of the output does get reflected at the input, and that parameter we are calling as HRE into VCE. That is the factor. HRE is a factor, and this is, so it is represented as a voltage source at the input. Similarly, at the output, we have a current source. Basically, here where what we see is the current amplification, the basic transistor phenomenon. So it is HFE times IB. Okay, it is HFE times IB. Now HFE is our beta. This F capital E capital stands for DC. Whereas H, when I say HFE, this is also called as beta AC. This is called as beta DC. So far we were concerned only with beta DC. Now, since we are talking about the AC signals, we will have this parameter into picture called as beta AC. It doesn't matter. We are not going to call this as beta AC. We're going to call it as HFE, lowercase f, lowercase e. All right. So this is the AC equivalent. This is the H parameter equivalent of a bipolar junction transistor in common emitter configuration. Okay. Now what we are going to do is we are going to replace the transistor over here. We are going to replace the transistor. This transistor we are going to replace with its AC equivalent circuit, with its H parameter equivalent, this one, and we are going to draw a new figure. But have you understood the concept of the H parameter equivalent? Yes.
Yes, sir.
Yes, sir.
This one very important, because without that we cannot go ahead. And interestingly, I must have told you that always why we are doing this, because we want the transistor to be modeled in terms of primitives or the basic building blocks. What are the basic building blocks? They are the voltage source and the current source, and of course the resistors. So you can see here, this is the voltage source, this is the current source. Do you remember the lecture on the current source and voltage source? No.
Yes, sir.
See, this is the place where you have to start revising the concepts. Otherwise, we'll be in deep trouble, I'll tell you. Okay, we'll first of all see the H parameter equivalent circuit. Now, this is the device. This H parameter is for this device. It is for this device. This circuit is for this device. But we have now having this device in addition to the other components also. So what we will have is an H parameter equivalent circuit for common emitter voltage amplifier. This was common emitter H parameter equivalent for bipolar junction transistor in common emitter configuration. So this is the device equivalent. What we are going to see now is the circuit equivalent. Okay, so bear with me while I draw the figure. So I'll draw it with okay, this color itself. Green. I'm just reproducing the H parameter equivalent. Now this is the transistor. I've completed the transistor. Okay, I'll label it in different color. So this is your base, this is your collector, and this is your emitter. This is HIE, this is HRE, VCE, this is HFE, IB, and this is 1 by HOE, output admittance. This is your base current, IB, this is your collector current, IC. Now let us talk about the external circuit. I will use different color for that. So here we will have so what do we have between the base and the AC ground? Remember, emitter is at AC ground always. Okay, so consider this as the AC. So we have resistors R1 and R2. We have resistors R1. We have resistor R2. So this is R1. This is R2. Okay. Similarly, at the output, I have resistor RC. There is no RE. Okay. Okay, up to this point. Then I have the loads. I have the load. Here I have output voltage, which is to be developed across the load. This is actually where your current flows IC. I'll just remove it from here. Okay. To be more precise, it flows here like this. So this is going to be your IC. IB is fine. Use the same color. Which is one and the same. Okay. Then at the input side, I have signal source. This is your BS. This is your RS. Now here I'm going to show polarities VI. This is the input. The source current flows here like this, IS. The load current IL. The other way around, because we see that the output is inverted, that is 180 degrees out of phase. So this will be minus plus, and the load current will flow like this. We are not interested in the load current at this point of time. So have you understood this circuit?
Yes, sir.
Yes,
Okay.
sir.
There is one more thing which we should see now, and that is Okay. If you look into this part, whatever is the impedance, is called as ZB. If you look from here, the impedance that you see is ZC. Why it is ZB, ZC? What are these? These are the device input and the output impedances. Device, the green thing. But over here, if you look from here, what we see is the circuit input impedance ZI. From here, if you look, it will be circuit output impedance Z. Is this concept clear to all of you? This is very, very important. Okay?
Yes, sir.
Okay. Similarly, I can draw AC equivalent circuit for common emitter amplifier with unbypassed
RE.
Yes, so I'll draw that because we are running out of time. So I'll draw that first. Remember, this is your emitter terminal. This is your base, this is the collector. Now I am having a slight variation here. This is your AC ground. So your emitter resistor now appears to be here. Other resistors will be as the previous diagram, R1, R2. This is going to be HIE, again HRE, VCE, HFE, IB. This is going to be IB. This is going to be IC. Again, this is going to be your RC. This is 1 by HOE. Then you have your usual connections for the input, RS, VS, and the load. Here again you have output voltage bit. Here you have input voltage. Okay. So what is the change that we have here? Is only this RE is connected here like this. Okay. And what is this value of IE? IE is nothing but IB plus IC. Remember this. Okay. So what we have seen here is there are two variants now. That is the H parameter equivalent with bypassed RE and H parameter equivalent with unbypassed RE. Please revise these two diagrams and the AC equivalents before we start tomorrow. All right. I think we have already run around time. If there are any doubts, any questions, please ask me immediately. Otherwise, we will stop here. Any doubts, any questions with these things, whatever we have seen today? Somebody wants to say something? Yes? So shall we stop today?
Yes, sir.
Okay.
Yes, sir.
Okay. Thank you.